Before the Claas Dominator 106 ever entered the field, grain harvesting across much of Europe was defined by limits that farmers could not solve on their own. By the late 1970s and early 1980s, farm sizes were increasing, crop yields were improving, and harvest windows were becoming tighter. Weather patterns were less predictable, labor availability was shrinking, and every lost day in the field translated directly into lost grain. Traditional harvesting methods, even when mechanized, struggled to keep pace with this new reality. Many farms still relied on smaller combine harvesters designed for conditions of the 1960s. These machines worked adequately on modest acreages, but their throughput was limited. When crops were dense or straw was tough, forward speed had to be reduced to prevent losses or blockages. Operators compensated with longer working days, higher fuel consumption, and increased mechanical wear. None of these responses addressed the core problem: capacity. Labor compounded the issue. A single combine required multiple support roles: grain transport, unloading coordination, maintenance. Yet rural labor pools were shrinking. Seasonal workers were harder to find, and training new operators on increasingly complex machines took time farmers did not have during harvest. The result was a system vulnerable to delay at every step. Crop losses were another unresolved challenge. Overloaded threshing systems led to incomplete separation. Grain losses at the straw walkers increased as operators pushed machines beyond their intended design. Spillage during unloading and frequent stoppages added to the total. Individually, these losses seem small. Across an entire season, they represented significant economic damage. Maintenance was equally problematic. Older machines demanded constant adjustment as conditions changed throughout the day. Belt drives, mechanical linkages, and manually controlled systems required experience and attention. A minor misadjustment could reduce output dramatically. Breakdowns during peak harvest were common, not because farmers neglected maintenance, but because machines were operating at the edge of their capability. Manufacturers, including Claas, understood these pressures. Farmers were not asking for comfort or luxury. They needed reliability, higher throughput, and stability across variable crop conditions. They needed a machine that could absorb the increasing scale of agriculture without demanding proportional increases in labor, time, or risk. At this stage, however, those needs remained unsolved, waiting for an engineering response that had not yet fully taken shape. This unresolved tension set the baseline for change. Farmers adapted with improvisation, but improvisation had limits. What the industry lacked was not effort, but a step change in machine capacity, control, and consistency. That gap, visible every harvest, defined the problem space engineers would soon confront. The core issue was not that combine harvesters failed entirely, but that the dominant designs of the time were reaching structural limits. Most machines available to European farmers were evolutions of concepts developed decades earlier. Incremental improvements had been added: slightly wider headers, marginally stronger engines, better cabs, but the underlying architecture remained largely unchanged. As harvest demands increased, these machines revealed weaknesses that could not be solved through adjustment alone. One constraint was the balance between throughput and separation quality. Conventional combines relied on relatively narrow threshing systems paired with straw walkers of limited length. When crop volume increased, grain separation suffered. Operators could slow down to maintain acceptable losses, but doing so undermined the very purpose of mechanization at larger scales. Speed and quality were in constant conflict. Power availability also became a limiting factor. Engines that were sufficient under average conditions struggled in heavy crops or damp straw. Power reserves were minimal, leaving little margin for adverse weather or high-yield fields. When machines were pushed harder, fuel consumption rose sharply, thermal loads increased, and reliability declined. These were not isolated failures, but predictable outcomes of operating near design limits. Machine size presented another contradiction. Smaller combines were easy to transport and maneuver, but lacked capacity. larger machines existed, particularly in North America, but they were often unsuitable for European field sizes, road infrastructure, and regulatory environments. Importing or adapting them introduced new compromises rather than solutions. Competitors such as John Deere and New Holland faced the same engineering constraints. Each offered strong machines within existing categories, but none had yet redefined what a mid to large combine should be for European conditions. Improvements were incremental because the risk of radical redesign was high. Farmers depended on reliability above all else, and manufacturers were cautious. Another overlooked factor was operator fatigue. As harvest windows narrowed, machines ran longer hours. Noise, vibration, and constant manual adjustments took a toll on operators. Fatigue increased the likelihood of mistakes, improper settings, and missed maintenance issues. The machine did not fail in isolation. The system around it degraded under pressure. By the early 1980s, it was clear that simply refining existing designs would not close the gap. Farmers needed a machine that could handle higher throughput without proportional increases in stress, mechanical or human. The existing generation of combines had reached a plateau. They were reliable within known limits, but agriculture was moving beyond those limits. The question was no longer whether change was needed, but who would risk redefining the machine to deliver it. Inside Claas, the growing gap between agricultural reality and existing machines was treated as an engineering problem, not a marketing one. Field reports from dealers and long-term customers were consistent. Farms were expanding, crops were heavier, and the cost of downtime during harvest was rising sharply. The company's existing combine range performed well within its intended scope, but that scope no longer matched how farms were operating. The response would require more than a revision. It required a rethinking of scale. Engineers began by defining the real constraint: stable throughput. Increasing cutting width alone was insufficient if the threshing and separation systems could not process the incoming material without losses. Likewise, adding engine power without strengthening the driveline and crop flow would only move failures downstream. The goal became balance, matching intake capacity, separation area, power delivery, and durability so that none became the dominant bottleneck. This approach shaped the concept that would lead to the Dominator 106. Rather than positioning it as an extreme outlier, Claas aimed to create a high-capacity conventional combine that remained compatible with European farming conditions. It needed to fit on existing roads, work on irregular field shapes, and operate efficiently across a wide range of crops, from dry cereals to tougher, higher moisture harvests. A key decision was to scale up proven systems instead of replacing them entirely. Claas had extensive experience with conventional threshing drums and straw walkers. Engineers chose to increase their size and robustness while refining crop flow to reduce peaks and dead zones. This minimized risk while still delivering a meaningful increase in performance. Powertrain selection followed the same philosophy. The machine required a stronger engine, but not one operating at constant maximum output. Reliability under sustained load mattered more than headline figures. Cooling capacity, belt drives, and gearboxes were all designed with reserve margins, acknowledging that harvest conditions are rarely ideal. Equally important was serviceability. Engineers understood that even the best machine would fail if it could not be maintained quickly in the field. Access points, modular components, and simplified adjustment mechanisms were prioritized early in the design process. These were not aesthetic choices. They directly influenced uptime during harvest. By the time the concept solidified, it was clear that Claas was not merely adding another model to its lineup. The Dominator 106 was intended to sit at the upper edge of conventional combine capability, absorbing the pressures that smaller machines could no longer handle. It was a calculated response to a system under strain, designed to restore stability rather than chase novelty. When the Dominator 106 first appeared, its reaction was shaped as much by appearance as by specifications. Farmers were accustomed to a certain visual logic in combine harvesters, proportionate bodies, modest heights, and a clear lineage to earlier machines. The new model disrupted that familiarity. It was larger, taller, and more imposing than many expected from a conventional combine designed for European farms. To some, it looked excessive. To others, it looked mismatched to narrow roads and smaller fields. The visual difference was not accidental. The machine's increased height and length were direct consequences of engineering priorities. Larger threshing components required more internal volume. Extended straw walkers demanded length. Expanded grain and fuel tanks needed vertical space to avoid compromising ground clearance or service access. From the outside, these choices appeared unconventional. From the inside, they reflected a deliberate redistribution of space around crop flow. Another point of skepticism was weight. Heavier machines raised concerns about soil compaction, especially in wetter regions. Farmers questioned whether the gains in capacity justified the risk. Claas engineers addressed this not by minimizing weight, but by distributing it more evenly. Axle loads were managed within regulatory limits, and tire options allowed pressure to be adapted to conditions. Still, perception lagged behind intent. The cab position also drew attention. Elevated for visibility over wider headers, it altered the operator's sense of scale. For experienced drivers, this required adjustment. Judging distances, aligning with crop rows, and maneuvering near field edges felt different. Early adopters reported a learning curve, not because the machine was less precise, but because it was more capable than what they were used to controlling. Even sound and motion contributed to the impression of something unfamiliar. Larger rotating masses behaved differently under load. Acceleration and deceleration felt heavier, more deliberate. This was not a flaw, but it contrasted with smaller, more reactive machines. The Dominator 106 communicated its capacity through inertia as much as through output. Over time, these wrong proportions began to make sense in use. The machine looked the way it did because it solved problems that were previously hidden behind slower speeds and longer hours. Its form followed function closely, even when that function challenged expectations. What initially appeared oversized was, in practice, appropriately scaled to the demands farmers were already facing. At the core of the Dominator 106 was a technical layout designed to increase throughput without abandoning the conventional combine principle. Claas did not introduce a radical new harvesting concept here. Instead, the company expanded and reinforced known systems, pushing them to the upper practical limit. This decision defined both the strengths and the boundaries of the machine. The engine sat in a power class that was considered high for European conventional combines at the time. Exact output varied by market and year, but it was generally in the range typical for large six-cylinder diesel engines of that era. More important than peak power was torque stability. The engine was selected to maintain consistent output under fluctuating load, such as when crop density changed suddenly or straw moisture increased late in the day. The threshing system followed a classic layout: a large diameter threshing drum paired with a concave designed for adaptable settings. Drum width and diameter were increased compared to smaller models, allowing more crop to be processed per rotation. This reduced the need for extreme drum speeds, which in turn helped limit grain damage. Separation continued through long straw walkers, providing sufficient area for grain to fall through even at higher feed rates. Grain handling reflected the same emphasis on continuity. A larger grain tank reduced unloading frequency, while unloading augers were sized to empty the tank quickly without excessive engine load. This improved field efficiency, especially in large plots where support vehicles could not always be positioned immediately. The drive system relied heavily on belts and mechanical transmissions, typical for the period. While this required regular inspection and maintenance, it also meant that repairs could be carried out without specialized electronic tools. Adjustments for different crops were largely mechanical, relying on operator experience rather than automation. Limitations were inherent. As a conventional Walker combine, performance still declined in extremely high yield or very wet conditions compared to later rotor-based designs. The machine demanded correct setup. Incorrect concave clearance or drum speed could negate its advantages. Fuel consumption increased noticeably when operated continuously near maximum capacity. Despite these constraints, the Dominator 106 achieved what it was designed for: sustained, predictable throughput within realistic operating margins. It did not eliminate the laws of physics, but it shifted them enough to make a tangible difference in daily harvest output. The first real test of the Dominator 106 did not happen in brochures or factory yards, but in fields under harvest pressure. Early units were delivered to farms that already knew the limits of their existing machines. These were not experimental plots, but working operations where delays had direct financial consequences. The expectations were cautious. Farmers were less interested in innovation than in whether the machine could simply keep running when conditions deteriorated. Initial reactions focused on capacity. Operators noticed immediately that forward speed could be maintained longer as crop volume increased. Where previous combines required frequent slowing to avoid losses or blockages, the Dominator 106 absorbed heavier intake with fewer adjustments. This translated into more hectares completed per day, not because the machine was driven faster, but because it stayed within its optimal working range more consistently. Reliability during the first seasons became a central talking point. Breakdowns were not eliminated, but they were less frequent than farmers expected for a machine operating at this scale. When issues did occur, they were often related to setup or wear components rather than structural failures. These reinforced the idea that the machine's core design had sufficient reserves for its intended workload. Feedback also highlighted learning effects. Operators accustomed to smaller combines initially underutilized the machine. Conservative settings left capacity unused. Over time, confidence grew. Adjustments became more assertive, and throughput increased accordingly. This learning curve was a necessary phase, reflecting the shift from operating near the limit to operating with margin. Not all feedback was positive. In smaller or irregular fields, maneuverability was less forgiving. Transport between fields required planning, especially in regions with narrow roads. Fuel consumption, while acceptable for the output achieved, was higher than that of smaller machines, which mattered to farms with limited annual hours. Despite these trade-offs, early adopters reported a net gain. Harvest windows shortened. Weather-related losses decreased. Support logistics became more predictable because unloading cycles were longer and more regular. These practical outcomes mattered more than technical debates. Word spread through observation rather than advertising. Neighboring farmers saw fields cleared earlier than usual. Contractors noticed fewer stoppages. Dealers reported growing interest from operations that previously considered such a machine excessive. The Dominator 106 was no longer an abstract engineering concept. It was proving itself as a working solution to problems farmers had accepted as unavoidable. As the Dominator 106 accumulated seasons in the field, its real character emerged under conditions that brochures never capture. Harvest rarely happens on dry, level ground with uniform crops. Machines operate in dust, heat, mud, and sudden rain. It is here, in prolonged exposure to variability, that design decisions reveal their true value. In heavy soils, traction became a defining factor. The machine's weight, initially a concern, proved manageable when paired with appropriate tires and careful pressure management. In dry conditions, stability improved cutting accuracy and reduced vibration. In wetter fields, operators learned to balance load and speed to avoid compaction without sacrificing output. The Dominator 106 did not eliminate soil sensitivity, but it gave operators more control over how compromises were made. Crop diversity further tested the machine. Switching between cereals with different stroke characteristics required adjustments, but the underlying systems handled variation predictably. Tough straw increased load on the threshing drum and walkers, yet the machine maintained separation quality longer than smaller models. In damp conditions, where blockages were common on older combines, the larger internal volumes reduced critical choke points. Weather pressure amplified these effects. When rain threatened, farms often ran extended shifts. Long hours exposed weaknesses in cooling, lubrication, and operator comfort. The Dominator 106's cooling reserves proved adequate for sustained operation, provided maintenance schedules were respected. Operators noted that consistent performance late into the day reduced the temptation to push settings beyond safe limits, indirectly protecting the machine. Maintenance in real conditions remained a daily requirement. Belts, chains, and bearings demanded inspection, especially under abrasive dust. However, accessibility simplified routine checks. Downtime was not eliminated, but it was more predictable. Planned stops replaced emergency repairs, which mattered during narrow harvest windows. Contractors using the machine across multiple farms observed another effect: standardization. Settings that worked well in one field often transferred with minor changes to the next. This reduced setup time and increased daily efficiency. Over a season, these small gains accumulated into measurable output increases. The Dominator 106 did not perform miracles. Extremely wet harvests still imposed limits, and no conventional Walker combine could ignore physics. Yet, across varied conditions, it consistently shifted the balance in favor of completion rather than compromise. Its value lay not in peak performance on ideal days, but in its ability to deliver acceptable results on difficult ones, when harvest pressure was highest and options were few. As confidence in the Dominator 106 grew, its presence expanded beyond early adopters and into broader agricultural practice. What began as a cautious investment by larger farms gradually turned into a reference point for capacity planning. Farmers who previously structured harvest around machine limitations started reorganizing workflows around the assumption that higher throughput was achievable and reliable. Production volumes reflected this shift. Demand for high-capacity conventional combines increased, particularly in regions where full transition to rotary machines was still impractical or economically unjustified. The Dominator 106 occupied a specific niche, large enough to transform productivity, yet familiar enough to integrate into existing service and maintenance structures. This balance accelerated adoption. Competitors took notice. While direct copies were rare, design philosophies began to converge. Wider threshing systems, longer separation paths, and greater power reserves appeared across the market. Even manufacturers pursuing alternative concepts calibrated their machines against the output levels the Dominator 106 had normalized. It effectively reset expectations for what a conventional Walker combine could deliver. Dealers reported another pattern. Farms upgrading to the Dominator 106 often skipped intermediate models. Instead of incremental growth, they made decisive jumps in capacity. This reduced fleet diversity and simplified spare parts logistics. One primary machine replaced two smaller ones, reducing labor coordination and support equipment needs. Custom harvesting contractors amplified this effect. A single high-capacity combine could serve more clients within the same harvest window. This improved utilization rates and strengthened the contractor business model. As a result, the machine influenced not only individual farms, but also service-based harvesting structures. Training and knowledge transfer adapted accordingly. Operators developed new benchmarks for acceptable losses, forward speed, and daily output. These benchmarks spread informally through observation and discussion. The machine became part of a shared reference framework, shaping how performance was evaluated even on other equipment. This phase marked the transition from innovation to normalization. The Dominator 106 was no longer judged on novelty or appearance. It was judged on how effectively it allowed farms to scale without multiplying complexity. By embedding higher capacity into routine operation, it helped redefine efficiency not as maximum speed, but as sustained, repeatable progress through the harvest season. The broader impact of the Dominator 106 cannot be understood only through machine performance. Its real influence emerged in the economic structure of harvesting and, by extension, in how food production systems began to organize themselves around higher capacity equipment. When a single machine can complete more work in less time, it changes not just field operations, but investment decisions, labor allocation, and risk management across entire regions. At the farm level, the most immediate effect was reduced harvest duration. Shorter harvest windows meant less exposure to weather risk. Grain quality improved simply because fewer fields were caught by late-season rain. This had downstream economic consequences. Higher quality grain achieved better market prices, which improved farm stability over time. The machine did not increase crop yields directly, but it increased the proportion of yield that could be successfully recovered. Labor structures also shifted. Fewer machines were needed to cover the same acreage, which reduced the number of operators required during peak season. However, those operators became more specialized. The complexity and scale of a Dominator 106 meant that experience mattered more than ever. Skilled operators could extract significantly more performance than inexperienced ones, reinforcing the value of technical knowledge in agriculture. On a regional scale, contractors expanded their role. High-capacity combines made it feasible to service larger geographic areas within tight harvest windows. This encouraged consolidation of harvesting services and increased mobility of machinery fleets. Farms that previously relied on local labor began integrating into broader service networks, effectively industrializing a process that had once been highly fragmented. Manufacturers observed changes in purchasing behavior as well. Investment decisions increasingly prioritized throughput per machine rather than fleet size. Instead of buying multiple smaller combines, farms opted for fewer, larger units. This altered production planning for manufacturers and shifted demand toward higher specification components, stronger drivetrains, and larger crop handling systems. There were also systemic effects on food supply chains. More predictable harvest timing improved the logistics planning for storage facilities, transport companies, and grain processors. Bottlenecks shifted away from the field and into downstream infrastructure, revealing new constraints in storage capacity rather than harvesting capacity. In this context, the Dominator 106 represents more than a single model. It sits within a broader transition in agricultural engineering, where capacity scaling became a central design objective. Its influence is visible not only in machines that followed, but in the assumption that harvesting efficiency can be engineered upward in meaningful steps, rather than improved only through incremental refinement. Years after the first Dominator 106 units left the factory, their presence in the field became less about novelty and more about routine reliability. On many farms, the machine blended into the background of harvest operations, doing its work without attracting attention unless something went wrong. Yet the absence of attention was itself a measure of success. In agriculture, the most valued machine is often the one that simply completes the season without interruption. Returning to an early season field where smaller combines once struggled reveals the scale of change. Where harvest previously stretched across uncertain weeks, operations now followed a more compressed and predictable timeline. Fields that once dictated the pace of work were now processed within windows that allowed farmers to plan logistics with greater confidence. The Dominator 106 did not remove variability from agriculture, but it reduced how often variability turned into crisis. Over time, older machines that defined earlier eras of harvesting were gradually retired or reassigned to smaller roles. Their limitations became more visible in comparison. What once required careful coordination and long working hours was now handled with fewer machines and less stress on labor resources. This transition did not happen abruptly. It unfolded gradually as farms made economic decisions based on maintenance costs, uptime, and output consistency. Even as newer generations of combines entered the market with advanced features and updated technologies, the Dominator 106 remained a reference point. Not because it was the most advanced machine in every category, but because it marked a clear shift in expectations. After its introduction, mid to large-scale harvesting capacity was no longer seen as exceptional. It became the baseline against which improvements were measured. In hindsight, the significance of the machine is not tied to a single innovation, but to the aggregation of many engineering choices working in alignment. Larger separation area, stable power delivery, serviceable design, and predictable field behavior. Each element alone was incremental, but together they produced a step change in operational capability. The story ends where it began, in the field. Not with dramatic transformation, but with quiet normalization. The Dominator 106 becomes part of the landscape of modern agriculture, representing a point where harvesting stopped being constrained primarily by machine capacity and started being defined by how effectively that capacity could be integrated into larger systems of production.